Dr. Saurav Chakrabarty, working as an associate professor in the computer science group at the Chennai Mathematical Institute, Tamil Nadu. Before joining Chennai Mathematical Institute, he was a postdoctorate at the Algorithms and Complexity Department of CWI, Amsterdam, Netherlands. He was a postdoctorate at the Computer Science Department of Technion, Israel. He was awarded PhD in Computer Science from University of Chicago. His area of research is theoretical computer science. His focus has been in the classical and quantum complexity of Boolean functions, including property testing, sensitivity, block sensitivity of Boolean functions, and quantum database search in electronic commerce, in graph algorithms, and in coding theory. He has published several research papers in both national and international journals.
Welcome to the UGC lecture series in computer science, and the topic is algorithms. So, today we will be looking at more of dynamic programming. In particular, we will be looking at these two problems known as the edit distance problem and the knapsack problem. As we told last time that one of the biggest problem of algorithms is to understand which algorithm or which problem should be solved using which technique, and the only way of getting a good handle on that is by trying out more and more problems. So, we have been given two sequences of symbols, and the question is that how many edits are necessary to convert one sequence to another, and what are the edits that are allowed? I can delete a bit, I can add a bit, or I can change a bit. So, in other words, I can delete any bit from one of this string, I can add a bit anywhere I want, or I can change a bit wherever I want. Each of them cost 1 rupee. Question is that how many edits do you need to convert one sequence to the other? So, for example, here say I have the string 1 snowy and string 2 is sunny. Now, I want to convert string 1 to string 2. One thing that one can do is that I can delete one by one everything here, and then I add S U N N Y. So, I will make 5 deletes and 5 adds. So, it will be cost me 10 units, or I can do something more simple. I can say add a U over here, add U. I can change this one to N, and I can delete this one. So, I will have 3 moves that will convert snowy to sunny, and similarly I can do many other such kind of stuff. So, how many edits will I need? The question, how many total amount of things that I will need. So, another example is these two strings, say exponential and polynomial. Now, how do we do it? See, here we can do various things. We can say maybe delete these two things, then we can add L and Y over here, and then we can change this one to O, this one to M, and I can remove this one. So, I will have 1, 2, 3, 4, 5, 6, 7 moves that will convert polynomial to exponential. Because for example, P O L Y N O M I A L polynomial we will get. We can maybe do something more interesting. For example, say convert this to M, this to O, I remove this one, and then I convert this to Y, this to L, this to O, and this to P. Let's see, P O L Y N O M I A L, and again it makes 7 moves. Now, question is that what is the smallest number of moves that can be made to convert one string to the another? So, this problem is called the edit distance problem, and this also has enormous set of applications. Of course, it has applications to computational biology kind of areas where we want to change, understand the distances between DNA sequences. Also, there is a notion of edit distance between trees, something that I will not be able to describe in this lecture, but the edit distance does not need to always be between sequences, it can also be between trees and so on. How can you convert a tree to another tree and so on, and it is very useful for various real life applications. So, the question is, given A1 to An and B1 to Bn, what is the smallest set of edits that changes A1 to An to B1 to Bm? Let us first try the brute force approach. Consider all possible sequence of edits. Now, this is where we get stuck completely. If you remember the longest common subsequence problem, there we had looked at all possible subsequence of A1 to An, and the total number of possible subsequences were 2 to the power n. But here what is the all possible sequence of edits? They can be basically anything, because we can add and delete any amount of stuff. So, sadly enough, the total number of possible sequences can be unlimited. So, this approach has to immediately be forgotten. This is a case where brute force approach just does not work, because it does not seem to have any limitations on the number of sequences that we have to consider. So, this is not good at all. In the second approach, let us go for the recursive approach. This is very similar to the longest common subsequence problem, but we define this thing called EDIJ. This be the smallest sequence of edits that converts A1 to AI to B1 to Bj. Again, why did we define this particular function EDIJ? It is because of our experience. We had experienced it in our last many lectures that defining this sub problem in this way helps us to call a recursive algorithm or design a recursive algorithm by recursively calling EDIJ. Of course, we need to prove it by giving the real right recursive calls. One thing to note here is that what is EDK0? EDK0 is basically saying that how many edits do you need to convert A1 to AK to the empty string. Now, clearly if I have A1 to AK, I need to delete all of them, and that must be the minimum one. So, that must be equal to k, and similarly ED0k means I have an empty string, and from that we have to design B1 to Bk. The only way of doing it is by adding B1 to Bk one by one. So, thus we get ED0k which is equals to k. To understand the recursive calls, let us look at these two strings sunny and snowy. Note that the output that we are looking for is ED 5, 5. Note that the last string. Now, the last string are same. If the last string is same, this algorithm basically says that if you can convert this remaining string to itself, then you do not have to worry about the last string, they remain same. And in other words, if the best set of edits converts do touch this y, then it must not be able to touch this y, and that is not good enough. So, there must be some set of edits that would leave this y untouched. So, in other words, I can write here that ED 5, 5 is equals to ED 4, 4, because the last string is same. Now, let us look at the next string to that, n and w. Now, this is where things become interesting. They are not same. So, what all possibilities can there be? The first possibility, n can be converted to w, and then it would be like, okay, now convert this remaining string to remaining string. Or the next one is that I can remove w n, just delete n. If I delete this n, then I will have to convert this the remaining string to this whole string. And the third one is that I will add a w over here, add a w after n. If I add a w over n, note that I have to convert this sunny to snowy. So, a w has to be added here somehow, either by removing n, or it will come out from somewhere after this, or something has to be added. So, or add w. If I add a w over here, then the idea is that I will get this w, and in that case I have to convert this s, the remaining string, to this string. So, in other words, ed 4 4 can be written as either you change n to w, in that case I get ed 3 3, or you remove n. So, in that case you change 3 to 4, the remaining thing to the fourth string, or you add a w, in this case you convert this 4 string to 3 string, and in each of them you have to have already done one of the edits. So, it is plus 1. So, this is the recursive algorithm that we have. So, the pseudocode of the recursive algorithm is first define the base case, then if a I equals to b j, then it is simply e d I j equals to e d I minus 1 j minus 1, else e d I j equals to I minus 1 j minus 1, minimum of all these three things plus 1. This is a very simple understanding of the pseudocode and recursive algorithm. But what is the runtime of this algorithm? The runtime of the recursive algorithm is just like in the other case. Note that we were calling for I j, we are calling either I minus 1 j, or j minus I j minus 1, or I minus 1 j minus 1. So, t of n equals to twice t n minus 1 plus t n minus 2 plus order 1, and which case you can see that we will get t n equals to 2 to the power order n. Again a pretty big number, it is an exponential number. So, that is not good for us at all. So, let us take a small break now. After the break, we will see how can we use the dynamic programming to get a better result. Welcome back after the break. Before the break, we saw the recursive algorithm, and we saw how the recursive algorithm gave an exponential time algorithm. But question is that can we do better? Yes, we can do better using dynamic programming. There are three different kind of dynamic programming: the divide and conquer algorithm, there is the greedy algorithm, and there is dynamic programming. And the dynamic programming, the idea is to decompose into small problems, just like in the case of recursive algorithm, solve the sub problems and store it in a table, and then combine these problems to get the answer to the bigger sub problems. So, we have already defined the sub problems. The E d I j was the sub problem, the base case was defined, and we have also done the how to combine the sub problems. So, the only thing that is remaining to be done is how to store it, and exactly here to store it one would like to store it in a table. So, here I have written it in these numbers, but you can think of the numbers as 0, 1, 2, 3, 4, 5, and similarly 0, 1, 2, 3, 4, 5, and basically anywhere here say 3, 2, this will contain E d 3, 2. And how do we go about it? First of all, we solve the base case. Note that the base case we know that E d 0 k is equals to k and E d k 0 is equals to k. And now, for the remaining ones, if these two are same, then this must be the diagonal one. So, in this case it is 0. If these two are not same, then it is the minimum of diagonal, top and bottom, the three things, and plus 1. So, in this case the minimum is 0. So, it will be 1. So, let us look at it. So, this is saying that how to convert S to S and U. and this basically says that you just remove u and you will get s. Similarly, here s is not equal to n. So, it is the minimum of these 3 plus 1. So, it is 2. Now, I will keep on adding it one by one. So, s and n is not same, minimum of this 3 plus 1. So, is 1. Here again not same, minimum of this 3 plus 1 is 1. So, now see here exactly again it happens. This is asking that how can we convert s and n to s and u, and since I have taken this diagonal one. So, this basically says that all I need to do is change the n to u. Note that there were 3 different options, either you can remove that n or add the u or change the n. The diagonal one represent the change. Similarly, here n and n are same. So, this must be just the diagonal one, which is 1. N and n are same. So, this must be the diagonal one, so, is 2. N and y are not same. So, it will be minimum of this 3 plus 1. O and s is not same. So, it will be 2, 2, 2, 2 and 3. Every time I am just looking at the all the 3 plus 1. W is also not same. So, it will be minimum of this 3 plus 1. So, 3, 3, 3, 3, 3. Y and y is not same. So, it will be minimum of this 3 plus 1. So, 4, 4, 4, 4, and here it will be same. So, it will be minimum. So, 3. Just to convert, we can convert snowy to sunny in 3 steps. So, here is the pseudocode of this dynamic programming. The pseudocode is exactly same, except that we have to store it instead of recursively calling it. The runtime, the algorithm stops after the whole table is full. The table contains m n spaces. Each space takes order 1 time to fill, because we are just looking at these 3 things and we are adding plus 1. So, the runtime is order m n, much better than 2 to the power n that we had got in other ways. One important thing that we had repeated last time also, that how can we use this thing to understand the sequence of edits. Let me go over this whole table once again. Just to start with the base case, let me just add this one. So, this is the base case that we had. Now, from everything else, what we will do is that we will, if s is equal to s, we know that it must have come from, then we have to look at the diagonal one and not add anything. So, we add a diagonal one and I put 1. Now, when we come here, we take the minimum of these 3 and add 1. So, maybe minimum of this 3 and add 1 is 2. Minimum of this 3 and add 1, say, it does not matter which one I choose. Minimum of this 3 and add 1, say, minimum of this 3 and add 1 is 5. I am just trying to do it in some random order. Say n here again, we have to, since it is not equal. So, you take the minimum of this 3 and plus 1, maybe it is 2. Here it is minimum of this 3 and plus 1. So, here I have to go down and that gets 2, minimum of this 2. So, this is n is equal to n. So, this 2 must come down from here and it will be 2. N is equal to n. So, it will be coming from there. So, it will be 3. N is not equal to n. So, it will be 4. So, basically I am just keeping a pointer about from where I am getting the answer. So, again here I have to take the minimum of this 3 plus 1. So, say minimum of this is 2 plus 1 is 3, same here 3, maybe 3, 3, 4. Here again say 4, 4, 4, 4, 4, and here again I do the same thing, 5, 5, maybe this one say 5, 5, and since y is equals to y, I go down here and get 4. Now, this is where I have not only these numbers, but also the arrows. Now, why that one helps? What we can do is that we can go back like this and we can obtain the actual number. For example, from here the first thing that I have done is go up, meaning, and since y is equal to y, meaning I leave that y as it is. So, I come here. From here this says that one thing to do is that we can remove this n, because we have gone down up. So, I delete this n. So, again we have gone up here, which means that n is not equal to O. So, I have n or changed n and I come here. From here I come here and I realize that from here, since I have just gone up one step, so I have not changed anything. So, I have come here, and similarly I go up here, means I have removed it one step. So, in other words, these arrows helps us to understand the set of edits that I have done. So, not only does this table helps us to store the whole information about the length of the smallest edit distance, but it also helps us to understand the actual set of edits. In the remaining time left, we would like to look at another problem, a very important problem called the knapsack problem. So, here we have been given a list of items with some volumes and some cost of each item, and a bag with some capacity, and the goal is to pick as many items as I can, such that the bag is not over full and the total cost of item that we have chosen or picked up is maximized. So, this is a typical problem that we face all the time. So, when I am going from one place to the another, maybe I have lots of important objects that I need to take, but I just have one box. Now, in this box some items can go, I mean every item has a volume and I cannot overfill the box, and every item has some cost associated to it. So, my goal will be to pack as many things so that I carry the maximum cost items. So, here say example, one simple thing that I have a object of 12 kgs and the cost is $4. I have a object of 1 kg and cost is $2. I have 4 kgs and cost is $10 and so on, and I have a bag that is called the knapsack. I have a which can only accommodate 15 kgs. Now, how many quantity or how many value can I choose? What is the best set of values that I can take? So, in other words, I will be given a set of items, item 1, item 2, item 3 to item n items. Each of them will have a volume and a cost associated to it, a volume and a cost, a volume and a cost, and we have given the capacity of C. The goal is to pick some S items such that total volume of object picked is less than C and the cost of object picked is maximized. So, this is what is most important. I want to maximize the total amount of object picked under the condition that I can carry them in my bag. Now, how do we do it? In general, this problem is very hard. We will talk about it in next couple of lectures, but we can use dynamic programming to solve some instance of it. Say for example, we have this say the items I 1 to I n, and let k s I c be the maximum cost of item that can be picked in a bag of capacity C when the items are I 1 to I i. So, this is the sub problem that we are looking at. Now, clearly if I have no item, then I cannot pick anything. So, k s 0 c is 0 and k s I 0 is 0 if the bag's volume is 0. But the recursive thing is here that either I K as I C, either the best that I can do might not even take the ith element. In that case, it is equal to K as I minus 1 comma C, or it has picked the ith element. So, it is I minus 1 comma C minus V I, because I have eaten up the volume of the ith element. So, this gives us another dynamic programming approach to this whole thing. So, we will have this using the same idea, we can solve this table all by itself. So, at this point we have to jump not from just looking at its neighboring sets, but we have to look at K I minus 1 something much further, C minus V I. So, this is a dynamic programming instance where again we have to solve each space by looking at only few spaces which have been filled, but need not be the adjacent ones. So, note that the number of spaces in this table is C times n. Each space requires order 1 time to fill, and so this total runtime is order n times C. Thus, for the knapsack problem, dynamic programming can solve it using order n times C, but the problem is that the input size of this problem is you have been given these n objects and you have been given C, but the C is given in binary. So, it is log C. So, it is n plus log C, but here we are using C. So, the runtime is actually polynomial in the input size only if this C is very small. If C is a very big number, then we cannot expect to get a polynomial size algorithm. We will come back to this particular understanding of polynomial versus exponential in the next couple of lectures. So, with this we come to the end of this lecture. In the last two lectures, we have seen dynamic programming and some examples of that. In this lecture, we have seen edit distance and knapsack problem. We have tried to understand when does dynamic programming help in solving a problem, and how can we use the dynamic programming to obtain not only the smallest length of the edit distance, but also the actual edit distance and so on.